Hello, today we're going to talk about Rust and .NET efficiency. I'm a big fan of C# and .NET because of how efficiently I can write code. I built my Lambda dispatch project using C#, and I hit a big problem at the end. The CPU usage to keep one Node.js worker at 100% CPU was 4 times higher than the CPU usage used by Node itself. That's not good. I have 2 components that I'm passing the traffic through, the router and the extension, both originally written in .NET. I found 2 simple changes you can make. One is controllable via a .NET environment variable that you can easily set, which is the spin count. I'll show you how to set that. The other is to control the number of maximum threads in the thread pool used by .NET. I ultimately rewrote one of these components in Rust. I rewrote the extension in Rust. And this is where it gets interesting. The CPU usage in Rust was equivalent, almost equivalent, to what it was in .NET. Now, everybody says Rust is supposed to be super energy efficient, and this shows you can't just assume that. You need to pay attention, and you need to evaluate, is this CPU usage amount versus the amount that Node.js is using, is this justified? In this case, the extension is doing twice as much work as the Node.js app because it is receiving a request and it is opening a request. So it's handling the traffic twice, whereas the Node app is receiving a request and sending a response and not making a subsequent outgoing request. So it could make sense if Rust was exactly as efficient as Node that Rust would use 2x more CPU, but not almost 4 times more. That doesn't make any sense. I showed in another video how to fix this. It has some limitations. It controls the maximum throughput you can achieve through a single Rust process, but it does alleviate high CPU usage at the same throughput rates. So it's something to look into. Your experience may vary, but I encourage you to explore these settings and evaluate the CPU usage of both your .NET and your Rust applications and see if you need to make some adjustments. Let's go through these real quick. The defaults are that .NET is going to use 12 worker threads on a M2 max with 12 cores. It's going to set the IO completion port threads to a minimum of 1, a maximum of 1,000, and the worker threads have a maximum of 32,000. In that case, we use 450% CPU to proxy the traffic to this Node.js app, and we achieve 15.5K. When we switch to the Rust rewrite, the CPU usage barely changed, and Rust by default in the Tokio async runtime is going to use 12 threads. The CPU usage of the router went up slightly, the throughput overall went down, and the CPU usage of Node didn't really change. If we restrict Rust to 1 thread, we get a higher throughput rate. The router goes bananas and uses all of the additional CPU that was freed up by the Rust extension, changing it to 1 thread. So we're now at 740% CPU to keep one process of Node busy. That's bad. Now if we set the .NET spin limit on the router, we get a little more throughput, not really significant, about the same CPU usage with Node. We cut the CPU usage of the router by more than 50%, and the CPU usage of the extension stays the same. And then the last change we make is we set .NET to only use 1 worker thread. We get the highest throughput, same Node CPU usage. We cut the .NET router CPU usage even further to only 120%. We make no change to the IO completion port threads. We just limit the worker threads to 1. If you set the IO completion port threads to 1, it has no effect. And the spin limit combined with this also has no effect. If you set the spin limit and you set the worker threads to 2, it's probably going to have an effect. But this, when it's set to 1, isn't going to have an effect. And the extension stays at 92%. In the next part of the video, I'm going to show you all of these being reproduced so you can trust that it's real. There are, of course, considerations. If you're going to set things to a single thread, you're going to max out at around 100% CPU usage per process. But you're going to be 85% more efficient. So you may be better off having multiple single-threaded processes in both .NET and Rust than using async and allowing the thread pool to have 12 threads on a 12-core machine. If you're on a single-core machine or a single-core Docker container, this isn't necessarily going to be an issue, but you're going to want to check that .NET and or Rust are both setting themselves to 1 or 2 threads in that case and not setting themselves to the number of CPU cores on the underlying machine. Let's dive into this and reproduce these results. Okay, we are going to reproduce the results on the board above For the 5 test cases we had, there will be variations in the numbers that we see versus what's on the board. They should only be about 5%. We're looking at 50 to 85% reductions in CPU usage though, so those should not be a big deal. So we're going to start the router with all the defaults. This is .NET. We're going to start the .NET extension with all the defaults. I'm going to send it one test request, and then we're going to hit it with OHA limited to one thread. You see the router's at 460% CPU, the extension's at 350 to 380, and Node.js is at 95. And the achieved RPS rate is 13,700, which is within range of what we got on the board. If we run it again, it's going to be a little faster. $15,300, that's pretty close. Okay, now we are going to show the Rust rewrite extension. We are using the default multi-threaded runtime from Tokio. The Tokio async runtime will create 12 threads on a 12-core machine by default when using the multi-threaded runtime. Let's see what happens here. We're going to send it one request, doing about the same 15,000 RPS. The router is about 500% CPU, and the Rust extension is at 320% CPU versus Node at 100%. That doesn't make a lot of sense, even with the Rust extension proxying the traffic and doing twice as much work to handle each request, receiving it and turning around and sending it, and then receiving a response and sending a response. That's still more than double the CPU of Node.js, which is odd. Let's go drop the Rust extension to use only the current thread. You see this environment variable here is controlling that. I'm just choosing how to start the Tokio async runtime. So we'll set it to one thread. We're starting the Rust extension limited to only using the current thread. And we're sending a test request. We get a test response. Now we're sending 10 concurrent requests, and we're up to over 18,000 RPS. The router is using 700% CPU, Node is using 110, and the extension is using 90. We freed up about 250% CPU, and the router took about 200 to 210% of that. You see the RPS rate is 18,000. Is that as good as it gets? No. The router, I can't change the extension, but I can change the router. The extension has a deadlock that I'd have to fix. But if we change this built-in environment variable for .NET to limit the number of semaphore spins that it will do when a thread is looking for work, we're going to drop it from, I think the default is 50 to 60 to 0. There will be no spinning anymore. We're going to start that router up. We're going to start up the extension limited to one thread again. We're going to send a test case or test request. Now we'll send 10 concurrent requests, and now the router CPU dropped from over 700% to 300 to 400%. The extension and Node.js are still doing the same thing. We cut the CPU over 50% by just limiting the spins on the semaphore at the end of a thread in the thread pool, completing its work. Now, let's stop everything, and let's instead limit the maximum worker threads in the worker thread pool in .NET to 1. You can make the same change with the completion port threads, but it has no effect. The problem is not the completion port threads. The problem is the worker threads. We're going to start this. We're going to start the extension limited to one thread. Send a test request. Now send 10 concurrent requests, and we're going to see, I don't know why it starts slow the very first time, but it gets up to 18,000 RPS now. Let's run that again, gets there a little quicker. The router's only using 120% CPU, Node's using 110, and the extension's using 90. So the router written in .NET is using about 30% more CPU than the extension rewritten in Rust. And that's the fifth and final test case. You should be able to use code like this to query the minimum number of threads, the maximum number of threads. You can set some environment variables to control how many threads you're going to use in .NET. Here are the functions you use to change the thread pool sizes, the mins and the maxes. And you can play around and try measuring the performance of your application. You can also use that existing built-in environment variable to limit the spins for thread pool threads that are looking for work. If you find that these change the performance of your application, you may want to consider using multiple processes instead of multiple threads within a single process. And that's it. Maybe you don't need to rewrite your app in Rust, though. Take another look. Thanks.